Welcome to qnawire.
Hi, so for this question, you are asked to just give like any value or any solid that you want to calculate its molar solubility. So first of all, just like as a small review, let's say that you have a solid that is formed in the following way, that is going to produce, when you put it in water, A amounts of the A compound, where A is the stoichiometric coefficient in aqueous solution. Here, the charge, it really doesn't matter for this example. The charge would be, in this case, for example, minus. And B amounts of B in aqueous solution. So here I'm omitting the charges. It really doesn't matter. Normally, you're going to have a charge over here. But in general, in order to find the molar solubility for any salt that you want, that follows a formula similar to this, you start with the solid. The amount of change, it is going to be minus S, the solubility of that compound, and at equilibrium, again, since we have the solid, it really doesn't matter. At the beginning, the ions on themselves, we don't take them into account, but the amount of S that is being produced is going to depend on the stoichiometric coefficient. So it is going to depend on these two numbers that we have on our chemical equation. So in this case, this would be AS, and in this case, it would be BS. So at equilibrium, you would have AS and BS. And if we write down the solubility product constant for this example, we would get concentration of A elevated to the A coefficient, concentration of B elevated to the B coefficient, which turns into AS to the A times BS to the B. And by solving this equation for S, you are going to be able to find the stoichiometric coefficient, the molar solubility. So let's just take a couple of examples. I'm going to pick up like one salt that is soluble. For example, solubility rules tells us that all lithium salts are going to be soluble. So let's take lithium carbonate, solid, which in water it is going to dissociate. Remember that the carbonate, it is going to be a complex ion. So we're going to produce two equivalents of lithium plus in aqueous solution, plus one equivalent of the carbonate in aqueous solution. Again, if we do our ice table, for this case, the amount that is going to change is the molar solubility of our compound. At the beginning, we have 0. For lithium, we're going to have 2s. For carbonate, we're going to have s as change. So at equilibrium, the quantities that we have are the following. If we look up on a table, the KSP for this compound, it is going to be 2.5 times 10 to the minus 2. And recall that this is equal to the concentration of lithium plus squared times the concentration of CO3 minus. If we replace this with the values for S, we're going to have 2S squared and S. This means that we're going to have 4S cubed. Thus, we can solve for S, that is the molar solubility. So S, it is going to be the value for KSP divided by 4 and taking the cube root of this. So the result in this case, it is going to be 4 0.184 molar. So you can add 0.184 moles per liter of this compound. Of course, that molar solubility, you can change it into grams per liter if you want, just by using the molar mass. So now we're going to do another example, but now with an insoluble salt. And that case, it is going to be, let's take, just to keep going the thematic of solubility rule, let's do silver iodide solid. So this is going to dissociate into silver plus iodide minus. Here, this is the most simple example that we're going to have for finding the molar solubility. Because our ice table, it is going to look as this. We are going to have minus S, minus the solubility, that is going to go into solution. We begin at 0. The change for both of them, it is going to be plus S and plus S. So at equilibrium, we have S and S. Writing down the solubility product constant for this compound, this is simply the concentration of Ag plus times the concentration of iodine. Of course, this is in aqueous solution, in case that you have a picky professor. And this is going to be S times S, thus S squared. So when we have a solid that is made up of only one cation and one ion, we have a one-to-one correspondence. The molar solubility, it is going to be equal to the square root of Ksp. Just in the case that we have a one-to-one correspondence in the solution. So for this compound, the value for Ksp, it is going to be 8.5 times 10 to the minus 17, which give us a value for molar solubility of 9.22 times 10 to the minus 9 molar. And those are two examples. So just as a small recap, here this is the general formula for solving for S for any possible solid that you may encounter. The only thing that is going to change is the value for A and B. And here I gave you two examples. One, in the case of a compound that is going to be soluble in water and is going to have a high solubility, the lithium carbonate, that follows solubility rules, because the first one is that group 1 elements are going to be soluble, and the second one was an example for an insoluble compound following another of the solubility rules that said that chlorine, bromine, and iodine compounds are generally soluble, with the only exemptions of silver salts, lead salts, and mercurium salts. And that will be all.